Hello everyone, this is lecture 8 of Advanced Drilling Engineering PTRE 451545. Let me make sure I'm recording. I am recording and I'm sharing the right screen because if there is nobody online, I want to make sure I'm doing the right stuff so that because nobody will tell me if I'm doing it wrong. So last time we went through a bunch of stuff including casing design. And some of you, it was the first time that you have seen it. I designed this class thinking that all of the students there have already done a drilling class before when I came over here. So it was a little bit, we don't spend a lot of time on that as much as we spend during the 411 class, but I think you understand how it worked. It has to do the mat window. Don't let the mat density go below a value at which corresponds to the pore pressure. And don't let the mat density go to a value high enough such that the bottom hole pressure corresponds to a value above the fracture pressure. And we're going to talk more about those today, in all honesty. We learned about two methods for casing design. The bottom up, we go up and to the left. And then we learn about the bottom down. They yield different results, and then we have to make a decision. We want our hole at the end to be as big as possible, and we want to use as less of metal as we can to pay less. And of course, we want to be safe. So we want to keep in a good safety margin as we did in this example. We also talked about some aspects of cementing, casing shoes invented by Carol Baker. We talked about float collar. We talked about the two cementing plugs. The bottom plug, which goes first, and is the red, and the top plug, which goes last, and it's black or yellow. Don't mix them up. You are gonna lose your job. That's about what we went through last time. And then we talked a little bit about some practical stuff. Obviously, if I have a casing that is 5-inch inner diameter, I'm not gonna run a 5-inch outer diameter in it, right? It will never pass through. I need to have a clearance. And practically speaking, this clearance, which is given by the ID of the outer tubular with respect to the OD of the inner tubular divided by 2, so the clearance, the distance between the outer diameter of the tubular inside and the inner diameter of the tubular outside should be between 0.13 and 0.18. And we have this kind of diagrams which basically tell us, okay, if I'm, let me write, if I'm at 4, I can run it through 5. And the 5, I can run it through 6 1/8, ideally 6.5. Dotted line is possible, solid line is recommended. It goes on like this. So if I want my well I design my well to have a 2 3/8 inch ESP in it. I need to make sure that my production casing or production liner inner diameter would be enough for me to run this pump down hole. And that means the intermediate casing needs to be bigger, and so on and so forth. So I need to basically make my planning properly. And I want to run as less number of casing strings as possible. So 3, if I can do it with 2, I prefer that, but of course I need to be safe. And we said last time I can do it with 2, but I need to get rid of the safety margin. And the safety margin is important because I really don't know how accurate my mat window is. Somebody gave it to me, and doesn't mean that he has data from every depth. right? And somebody designed it for me. It's not correct necessarily, but I hope it's good enough. Now, there are some ways, some tricks you can do to make it modern day tricks to be able to run less casing strings, like you can run it while run the casing while pumping, and at some point you are able to basically do lines that are not straight, they are like diagonal, and that helps you. It's a modern way of helping you use less casing strings. But again, it's the same principle. It's like you apply some back pressure and to help yourself with it. We're going to talk about some of this a little bit later. But in module 5, if we make it to module 5, which I think we will, and we're going to learn about a method for offshore to be able to use less casing strings, which is called in a managed pressure drilling method called DGD, dual gradient drilling. Hello, Rocky.
Yes, sir. My sound blasted. Sorry.
No worries. So we're going to learn about dual gradient drilling offshore to help you use less casing strings. But anyway, that about last time. So this time, today, we're going to proceed. And I think we're going to see the most important thing that you're going to learn in these classes from me, and that is the YouTube model. Okay, so we talked about how, well, we will talk about how to convert density to pressure. But you must already know, the undergrads certainly know how to convert, because in the oil field, I don't really know the bottom hole pressure necessarily, but I know my mud weight, right? And from the mud weight and the depth of the well, I can tell you the bottom hole pressure, right? And we will see the equation of how to do it. Some of you already know. You need to be you need to be able to convert mud density and depth to pressure and depth to mud density. And so I give you two, you can give me the third. That's the idea. And I want you to be very, very familiar with it. The YouTube model is basically a model for how the pressures vary throughout the well. Inside the tubular, inside the drill string and outside of the drill string. And you are gonna use it to derive the equations that you need to use to solve a problem. So it's applicable for basically everything, even except when you have fluids mixing with each other, then you need to make some corrections. It's still applicable, but you need to make some adjustments. So it doesn't matter how difficult the problem is. It will be a more complicated model, but you can still use the YouTube model to basically derive equations that you can use to solve your problem. So it helps visualize interactions between pore pressure and hydrostatic mud weight. The drill pipe is basically indicate. Let me draw something because it's gonna be easier for you guys to understand if I draw it. Okay, this is my well. This is earth. I drill my well. Doesn't matter if I have casing or not, but inside I have the drill string, okay? And then underneath I have the BHA, which has all the fancy stuff we talked about, okay? Logging while drilling, tools, drill collars. Jar is the word that was missing last time when I was telling you a word that starts with J that basically it has explosives. If you get stuck, you can turn it, switch it on, and it can hopefully vibrate your drill string and get it unstuck. All the fancy stuff, rotary steerable systems, etc., is generally thicker than the drill pipe and then the bit. Now, you have mud or fluids, different kinds of fluids, or any kind of fluid inside the drill string, right? Any type of fluid. And then you also have in the annulus. And the pressure changes all around the system because when you are drilling, you are pumping down the drill string and up through the annulus. Okay. The YouTube model has the left leg to indicate what happens inside the drill pipe. Okay? And the right leg to indicate what happens on the annulus. Between the legs is what happens here, the bottom hole pressure. Okay? And the bottom hole pressure, if you want to be balanced, needs to match. This is, let's just say, I cannot write there, this low. But this place here is the bottom hole pressure. It should match the formation pressure, which is here, under. So I think about it, bottom hole pressure is here, formation pore pressure is here. This needs to match this to be balanced. And then I also have a surface pressure on the drill pipe side and a surface pressure on the annulus side. This would be here and here. So this is how the model works. Okay. Let me clean. So the drill pipe forms the left leg, the annulus forms the right leg, and then you have DPP is the drill pipe pressure on the top left, and that is basically approximated by the standpipe pressure. If you are in the oil field and you are watching the EDR screen that shows everything, all the measurements taking place live, you will see something called SPP, and that's the standpipe pressure measurement. That's the last good pressure measurements you have before the mud enters the well from the drill pipe side. So we take this as the drill pipe pressure, DPP, basically. An approximation of that, a good approximation of that, I would say. Now, on the top right, you have the casing pressure, which is the pressure with which the mud exits the hole from the annulus. If it's open to the atmosphere, it means that this pressure would be 0 psi, okay? Atmospheric pressure, 0 psi-G or 14.7 psi-A. That is if it has to go through the mud return line, which generally is, as we said, open to the atmosphere. There are times when you have to, how do you call it? Where you want to use a fancy method like managed pressure drilling and you want to apply pressure there on the casing side, we call it back pressure. In that case, it won't be 0. But there is also a case where you receive a kick and you want to circulate it out of the well so that you don't have a blowout. In that case, you are going to shut the well. And if you shut the well, you are going to have both positive drill pipe pressure and casing pressure. And this is what you will have to play with to get the mud circulated out. So these values are very important because they are values that you know directly. They are on the surface, and you can have a measurement, an accurate measurement of those in the surface directly. So the surface pressures and the mud weight is something that you can know with certainty. Formation pore pressure, you don't really know it for certainly. You think you know it. You hope that what you know is good, what you think is accurate, but you are not really certain. And of course, if you know surface pressures and you know mud weight, you can very easily calculate BHP. Now, there is a case where you have more than one fluid on either side, okay? You may have 2 fluids in the annulus, 1 fluid in the drill pipe. You may have the opposite. it's still applicable. It's just more complicated equations. You may have 10 fluids, okay, with different density each. It's still applicable, but much more difficult algebraically. Okay. Now, if you have two fluids that are mixing with each other and they create a third phase of a different density, again, you can use it. It's going to be more complicated, but again, the same method. The first reference I have for the YouTube model, it was like a 1978 book called, what was it? Well controlled something, petroleum well controlled something. Anyway, so the bottom of the YouTube, yeah, indicates the bottom hole pressure. And this is the pressure at the bottom of the well calculated by the weight of the fluid in the well bore and any surface pressure above it. Okay. So this is the system, the circulation system that we saw before. Sorry, in a different picture, basically, when we are doing an overview of the circulation system. And it's exactly what I described before. These are the mud tanks. They suck mud into the pump gives it pressure. Okay, then it goes through the standpipe. This is where you take the measurement. And then it goes all the way into the, this is the rotary hose. It goes into the wash pipe, into the swivel, and then down the Kelly, down the drill pipe, up through the annulus, and then into the flow line, which is basically atmospheric pressure. That's why this flow line is inclined to use gravity to help you go back to the mud tanks to get cleaned up. So let's just see how it works. On the top left, you have DPP. This is basically the standpipe pressure. And on the top right, you have surface casing pressure. That is the flow line pressure. And then everything else varies with depth. So let's see. Yeah, surface pressure from the standpipe. And then once you are just ready to enter the well, P1, I show it again outside of the leg, above the leg, because you are not yet into the well, into the drill pipe yet. Then P2 is inside the drill pipe, so it's going to be in the left leg. But as you go deeper, there is more fluid above you, and this adds weight. Okay, the more fluid above you, there is more weight pressure in you, right? There is more, the deeper I go, the more weight I have above. Okay? Yeah. Yeah. So I go deeper. Now P3, look, even lower. Then PB, that's when I'm at the beat. At the beat doesn't have height. It's negligible height. But it has jets. And the jets are gushing mud out of them. So there is pressure loss from that happening in the jets of the jet nozzles of the bead. And we're going to talk about it in the next module, a lot about that, because the pressure losses at the bead are important. This is how they are used for making hole, to make the well. And then you're at the bottom of the well, bottom hole pressure. You want it to be equal to the formation port pressure so that you are doing it right. You are balanced. And then you have P4. Now you're on the other side. You are on the annulus. The annulus between the drill collars and the well, and the borehole. And then you get into a P5, which is the annulus between the drill pipe and the hole. It's basically bigger clearance. And then you get out of the well, you are in the surface casing pressure, which is atmospheric in this case. And that's it. So This is what you're gonna put together as an equations to solve it. But I did mention before that okay, I have fluid above me. It adds weight, right? If I have, and the weight, what do you think of the fluid above me in terms of pressure? What does it depend on?
Right.
So depth, yeah, and
Yes.
density. Okay. So, do you know what equation we're gonna use for that? Yeah? Yeah, rho GH. Do you know the conversion factor that we use for that in the oil field?
144.
No.
0.052.
0.052. Yeah. That's the most important equation for this class. So we always use the true vertical depth. We don't use the measured depth. Do you know the difference between the two?
Yes. The true vertical depth is
So this well
Ibris.
and this well,
So that's the measured depth.
well, they both have the same true vertical depth, but they don't have the same measured depth.
That problem.
Measured depth is how long the well is. It can be twisty, it can be whatever. Now, true vertical depth is how deep you go. And when it comes to, we said rho GH, which was absolutely correct, what we are using for the hydrostatic pressure, it's basically the true vertical depth that matters. Because if both wells are filled with the same density of fluid, they would both have the same bottom hole pressure. It doesn't matter that one is longer than the other. Now, if there is motion, and we're going to talk about that, there is friction losses associated. And one well is longer than the other. One well would have bigger losses to friction than the other. That would be a different story. But when it comes to hydrostatic, and I think I mentioned that in this class too, hydrostatic is a little bit of when we say the hydrostatic weight of this fluid column, we really mean the weight it does rho GH. Sometimes in the oil field we say, oh, the pore pressure of my reservoir is hydrostatic, and it implies that it's the same as if you had fresh water all the way to that depth. It's used interchangeably. So you have to make a judgment call when you hear the word hydrostatic. Sometimes it means fluid in general, sometimes it means fresh water. It comes from the ancient Greek word "idor" for fresh for water. That's why, but in science, it was routinely used to designate fluid. That's why all the stuff like hydraulic and whatever, they imply fluid or water. That's why it's used for. Anyway, so we have the density rho mat and true vertical depth TVD, and we are given this equation. So the mat weight in PSI at the bottom of TVD depth is going to be given by 0.433 PSI per foot. That is the pressure gradient of fresh water divided by 8.33 ppg. That's the density in oil field units, pounds per gallon of fresh water, multiplied by the density of the mud in ppg times TVD in feet. That becomes 0.052 TVD. Okay. Now, this 0.052 is a very famous conversion factor in drilling, very, very famous. So I want you to know it. I'm not going to give you that in an exam. I'm not going to give you 0.052, but I don't know why it's not writing. I'm not going to give you 0.052, but I will give you 0.433 and 8.33. You take one, divide by the other, you get it. So, but 0.052, you have to have it on the tip of your tongue because you are going to use it in your career if you do anything related to drilling and other stuff. Now, we're going to talk about this later. I think there is an example problem coming. Yeah. Calculate the pressure exerted by the mat of mat of density 9.62 ppg on the bottom of a 12,000 feet deep vertical well. So keyword here is vertical. I have a vertical well. TVD is 12,000 feet. Okay, it's filled with mud of, what is it, 9.62 ppg. Okay. I want to know the pressure here of the mat. So how would I solve it?
You multiply it by both with the conversion factor of 0.052, and then you multiply it by the total. Yeah.
And feet here, this is ppg.
That will be 6,001.
You don't really need a calculator for that because and I don't think I have the solution on the slide. This is because I know that this is my favorite mat weight. You know why?
No.
Because you multiply this by 0.052, it makes 0.5 or roughly 0.5.
Wow.
So that's why the 6,000 is the 6,000, which is correct. PSI. So because I need to take 0.052 times 9.62 and then times the TVD. If those two make 0.5, I just need to halve 12,000 and I get that. Now it's good to have this rule of thumb in your head because you know if your answer makes sense or not. So if it was 10, I will know that it should be weighing more than half the TVD. So if somebody was giving me, I don't know how much the mat weight would be if it was 10 ppg off the top of my mind, but I know it would be more than 6,000, right? Which is TVD divided by 2, right? If somebody was telling me it was 9 or 8.5, I know it should be less than 6,000, which is TVD divided by 2, right? Okay. Now, what if you are offshore?
Also, you have to consider the salt, the water. The water.
Yeah, very nice, very nice.
Because, yeah.
You have a water column, seawater column above you, which just like we did in, well, the undergrads haven't seen it yet, but in geomechanics, we do a lot of that. You have a water column above you. Now, when you're drilling offshore, okay, this is your water. And then you have your earth, but you have a well in it here. And you have a rig here, platform, whatever it is. And you are drilling, you have this marine riser. And then you have the well. Now, you have a certain fluid inside the marine riser, and then in the well. Sometimes it's the same fluid. But other times, it would be a different fluid. There is motivation to put inside the marine riser a different density fluid if you can. This is the basis behind the dual gradient drilling approach I was telling you earlier. We're gonna see in module 5, if you do this, you are gonna get easier casing design. And you want that, but you don't always have the facility to do that. Chevron has a drill ship dedicated to this task, because then you need to bring mud separately up from the well and mud separately up from the marine riser, etc., etc. It's a complicated process. But when we do the calculations that I mentioned earlier for mud weight or MW, we need to consider, do I have something like this or do I have something like this? Okay, if it's gonna be all purple, it means that I will tell you that at least the purple is heavier than the seawater. So it will take that into account. So let me erase. So what happens here? In offshore scenarios, need to add the weight of the overlying seawater. Let's just say the depth is DSW, and it will be, is this true vertical depth or is it measured depth? DSW, the depth of the seawater. Does it count as a measured depth or a true vertical depth? Have you seen sea going like? Yeah. But in the seawater density, now here is in PPG. It doesn't mean that I can give it to you. You will be given it in PPG. You may be given it in a different form, like specific gravity. Then you need to take that specific gravity and multiply the freshwater value with that. You may be given to it as a pressure gradient. Several ways it can be given to you. And then the density. Okay, so in this case, it's what I drew later. You have a different fluid inside the marine riser than below it. And I will tell you from now, and I won't explain why until the last module, that during dual gradient drilling, we want the marine riser to be filled with mud equal to the seawater density. Okay, this is the trick. It sort of cancels out the pressure from the water. In that case, you're going to use this equation here. 0.052 rho SW times DSW plus 0.52 rho mat TVD minus DSW. And that's assuming that you make the measurement of the depth from the platform. What if you don't? Then that would be just TVD. So again, different ways you can get inputs for this problem. It can be confusing. So that's why I don't want you guys to memorize equations. I prefer that you memorize methods. You're just trying to find out what fluid do you have and how much.
You said the TVD there is if you measure it from where? From the surface of the platform.
Yeah. You can. There is TVD BRT, small b. That means when you read drilling reports, they have this TVD BRT below rotary table. Okay, where is your rotary table? It's on the platform. But you also have sometimes TVD SS. Subsea.
Now it's starting from the.
So many times, yeah. And of course, it doesn't matter if it's a top drive rig, they still use BRT. Rotary table is like, it's an old tradition, they were using that. Also, you have this called Kelly bushing depth. It's the same thing, BRT basically. So it really depends, a lot of stuff. But it can be very confusing. And sometimes, yeah, you are not given things in the same units. Like here, you are given water in specific gravity, and then you need to multiply by 0.433, which is the pressure gradient of fresh water times the depth in feet to get the PSI value, and then the rest. Now, yeah, that if you are, this is for TVD BRT.
Yeah.
If it was TVD SS,
No need
that
to
would be just TVD SS. So in exams and homework, I make it clear. But if you are in the oil field, it may not be the case, or I guess offshore. If not dual gradient drilling is used, and this is most likely it won't, because dual gradient drilling is a cut-off technology of today. And the entire well and marine riser are filled with one type of mud, raw mud. Then with TVD measured from the sea floor or the mud line, that would be TVD SS. Mud line, we mean the sea floor. Okay, you use this equation. I think you understand why. Is the TVD from the sea floor below, and then the depth of the seawater, right? I will draw it. I will draw it. Now, it's this. This is my well. This is the mud line. It's the sea floor, basically, the mud line. This is the seawater. This is DSW. And then this is TVD. It's basically TVDSS. What I said earlier, TVDSS. And I have the same mud weight all the way. All the way. Sometimes they say DMR, marine riser depth, for that. Same thing, same thing. The seawater depth. These are estimations for static pressure loss. You do not consider any frictional pressure losses.
Well, the question made you understand that it's not a dual gradient drilling, or how will you?
Huh?
The questions make it clear to know whether.
Yeah. In this case, yeah, for sure. For sure. Most likely, in real life, it won't be dual gradient drilling. Most likely. These are estimations that include, so it's as if you are not moving, your mud is not moving. When your mud is moving, it's losing pressure also through friction. So yes, it gains pressure when you go deeper and it loses pressure when you go up, but you are also always losing pressure to friction. You need to take that into account. These equations assume you are not flowing. Okay, and your first homework that I posted yesterday also assumes that it's not flowing. Module 2, we are gonna start things moving.
Dynamic.
Yeah, exactly, dynamic mud weight. Example problem number 2. What would be the answer to example problem number 1 if the well was offshore, drilled under 5,600 feet of seawater? I don't need to tell you if it's TVD or MD, if it's seawater, right? Yeah, it's TVD. Assume that the seawater density is 9.27 and that the marine riser is filled with drilling mud. So how does that look like? I am in the sea. Seawater, we said is 5,600. It's fairly deep, right? And I have a well, and from the previous example, my well was 12,000 feet, right? 12,000 feet, it was TVD. It's from the bottom basically now because I just have 56. So I have what I had in problem number 1, but I have 5,600 feet of seawater above me. So the seawater density is 9.27 ppg. Does this matter? No, it does not matter. Because I have the marine riser, I have drilling fluid. So I have 0.052 times 9.62, which is my favorite mud weight, 12,000 plus 5,600. I add this up. What is it? 1760? 17,600. And I divide that by 2 because this times this makes 0.5, right? So it's basically 0.5 times 1760, which is basically, what is it? 13, sorry,
It's
67, something like that.
no,
6.8.
Oh, 8, sorry. Sorry. This, right?
No. 8,000.
Oh,
it's
8, 8?
yeah.
Okay. Like this?
Yeah.
Oh, okay. So, oh yeah, I don't have the answer because it's very easy. But yeah. Okay. Any questions on that? Donald, all good?
All good. Because
Okay.
he gave us the seawater density to confuse us.
Yeah. It's extra. Doesn't matter. It can be whatever. It can be whatever. It can be 10. It can be less. Doesn't matter. And if you notice, it was to make sense. Yeah, it's not in the problem yet. I'm telling you from now because you guys are understanding what I'm doing. If I do this method, I have to have seawater. I have to have my mud bigger than the seawater, regardless. If it's smaller than the seawater, it's as if I have negative pore pressure. It wouldn't work, basically. But I mean, yeah, it would be basically, how do you call it? This well actually is pretty, this example is quite, it's not as realistic as maybe it would have been realistic if the seawater is 8.5 or something. It should be much less to make sense because it basically implies that I'm drilling a well that is very, very low pressure. I'm drilling through a formation that is very, very low pressure. It must be depleted or something to make sense. But these are numbers I made up. Example problem number 3. What would be the answer to problem number 2 if the marine riser now was filled with mud density that is intentionally made to be equal to that of the surrounding seawater? This time, you are given that the density of the seawater is 0.465 psi per foot. This is difficult Gulf values. 0.5465 is Gulf value. So I have my seawater. It's still 5,600 feet, but it's also what is it? I want to put it here, 0.465 psi per foot, and I have the same well. As before, 12,000 feet through vertical depth, 9.62 ppg. But the marine riser, I will use a different color, is filled with seawater. And the seawater is the same as this, basically. I color it orange, but it's basically the same as the light blue, okay? 0.465. So now for my mud weight, let me use, I guess, green for UND. Mud weight is at the bottom of the well is 0.465 psi per foot, that's for seawater, times 5,600 feet, plus 0.052 in my wellbore below the mud line, times 9.62 times 12,000 feet. I forgot to put the units here. ppg times 12,000 feet. So I know this part is the same as example problem number 1. So it's, what did we say was it the answer then? 6,000, okay. So I only need to calculate the above. 0.465 times 5,600. What is this? If you just
2,604.
2,604.
Yeah.
So the answer would be 8,604. Excuse me. Right? The answer is correct? Okay. I don't think I have the answer to this either. I was so mean, I didn't put the answers. It's to force the people to learn the 0.052 conversion factor. And it's important to know it. One time I went to a rig to visit. I was a sophomore. I was taking my first drilling class in Texas. And it was a rig that was supposed to be automated. And we went to see it. It was a rig that was committed to Apache. And when we were there, it was a Cuban guy and a bunch of Dutch people, including a guy that he had already accepted a job to be the drilling professor in Texas. I remember we sat down and somebody asked a question like, it was like a question like this, like what would you use to how do you calculate the pressure, hydrostatic pressure for whatever? And I remember the drilling professor, well, before he became a professor, he was sitting with us and he said, yeah, you use that 0.052 equation. And it was like this. Now you also know that if that 0.052 is combined with 9.62, it makes 0.5. So you don't even need calculator. Okay. So how I will use my YouTube model now? We talk about the YouTube model, and now you know how to calculate how much hydrostatic column weighs. Now, how do you apply that into your YouTube model? Okay. Here you have a YouTube model that has two fluids in there. Okay. It's a well that has one fluid in the drill pipe and two fluids in the annulus. So how does it look like? It looks like a well it has drill pipe, BHA, bit all the way to the surface. Obviously, there is a surface pressure and on the drill pipe side and on the casing side. My drill pipe is filled with purple fluid, right? But my annulus is filled with purple fluid up to a certain point. After that, above, I have a different kind of fluid, yellow fluid. And when I say different kind of fluid, we really mean different density, okay? It can be two different fluids with the same density. I count it as one. I will count it as one fluid. But if it's different density, it's fluid 2 and fluid 1, okay? So this is what this means. This is what it implies. I will erase it because I need to go over the bullet points. On the left leg, I basically have, how do I calculate, what is the equation of the left leg? It's basically the drill pipe pressure plus this weight equals to formation port pressure, right? Because what is this? DPP plus the weight of this is what is it? It's on the,
Basically, the hydro.
huh?
It's basically it's the same as the hydrostatic.
No, yeah, it has to be. It has to be, but it's not always. What is it equivalent to?
By the way,
Yeah, what is on the mud weight where?
in the drip pipe. No.
Where on the drip pipe?
Surface.
No.
At the bottom.
At the bottom.
Is it the bottom hole pressure? Right?
Yes.
Yeah.
Okay. And this equation basically says bottom hole pressure is equal to the formation port pressure. Right? If I'm balanced, this must be true. Bottom hole pressure equals to the formation port pressure. That's the left leg. I have, so what, how many unknowns, how many variables I have? I have a DPP, I have a raw fluid 1, I have a TVD, and then I have an FPP. Generally speaking, when I'm drilling, I can see DPP is in front of me. I know raw fluid 1, right? I know it. And then obviously I know TVD, how deep my well is. But I don't really know FPP very well. I'm not confident that I know it very well.
Which one?
FPP, this one. It's what they gave me. It's like the mud window. They gave it to me. I don't know if it's correct or not. It might be a little bit wrong places to place, right? But I do know, I can know my BHP very, very accurately. And then if that is equal to FPP, I'm good. If not, I'm in trouble. What about the right leg? The right leg is a little bit harder because now I have two fluids. I have the surface casing pressure, but I have fluid 2 up to for this interval, and then fluid 1 in this interval. So the equation is much more complex, right? It's FPP equals to this weight plus this weight plus this pressure, right? So the weight of the purple would be 0.052 raw fluid 1 TVD minus D of fluid 2. And if I know this, it's good. I don't think I will know that in well-controlled situations easily. Plus the yellow. So let me just color it properly. This is purple, right? Okay. This now is yellow, 0.052 times this depth. And then CP, let me move this. CP is this here. Now, what is the right-hand side equal to? The right-hand side.
So it is also equal to the bottom hole.
Exactly. It's the same equation as here. So you see, it doesn't really matter if I went up, down. Sorry. I don't know what happened. It doesn't matter if I go up, down, or down, up, or up, down, and down, up here. It's the same balance, right? I always do FPP equals BHP. Always, always, always. And I can have 10 fluids here or 10 fluids here. It will still be the same method, right? More complicated math, more unknowns that I don't know with certainty, etc., etc. So it will be, it's the same method, right? Okay. Now, if I shut the well, like I said, these pressures become very important. They are important regardless, but they change the name. They are no longer DPP or CP. They are SIDPP, which is a very famous acronym in drilling, and SICP. It means shut-in drill pipe pressure, shut-in casing pressure. You still treat it the same, you just add it here. It's just gonna be called different. Okay, so they are very famous acronyms that we use. Like if you take a well control school, they're gonna be talking to you about SIDPP, SICP. This is what they mean. It's basically the pressure here and the pressure here. And there are gauges and you measure them. When you do the project on the drilling simulator 3, it's the same thing. You have values of them in front of you. Okay, any questions about the YouTube model? Okay, I think I have an example problem. Oh, go ahead.
Yeah. But if you have different fluids in the right hand side, let's say 3 fluids, the same thing, right?
Yeah, even in the left side,
Yeah.
same thing.
Yeah. So which means it means that those fluids, if they are of different, the 3 fluids have different density.
Yeah.
So it's the same thing that you're gonna do here, right?
Yeah, yeah. Here you have one fluid on the left drill pipe side, 2 fluids on the right side.
So assuming we have 3 fluids in the right hand side.
No, it's 2.
I'm assuming.
Oh, you want 3? Yeah, that's
Yes.
fine. But then you need to know the depth of each fluid, right? It's just you set up some algebraic equations and you see you have some unknowns and some knowns and you solve them. That's the whole purpose of the YouTube model. That's the whole purpose. You can have 10, you can have 20. It's just more complicated. You have more complicated situation because generally, not generally, always, if you have 2 unknowns, how many equations do you want to solve them? 2. Okay, YouTube model really gives you 2 equations, the left side and the right side. So you basically can deal with 2 unknowns. In well-controlled situation, D fluid 2 is unknown, and raw fluid 2 is unknown. DPP is known, it's SIDPP in that case. SICP is known, they are in front of you. You can have somebody recording it for you. Raw fluid 1 is very well known because that's what you mixed and put down whole. TVD is known. So basically, you have 2 unknowns, 2 equations, and you solve. If there is 3 unknowns, I need to give you another equation somehow, like with words, and you need to figure it out, which is not hard.
I want to
Okay.
ask a question. Is
Yeah.
it offshore? Is it applicable in any case?
Yeah. Offshore is like in between the surface drill pipe and when you start the YouTube model, you have the weight of the seawater. So you can add it basically at the column if you want. Depends on how, if you have a marine riser that is filled with mud, it's like this becomes a different, this becomes longer, let's say includes the marine riser, and so does this, and so does this. It's a balance. Or if you are using 2 different fluids, you can have a light blue portion here. If you want. Yeah, whether you have it outside the leg or inside, it's the same thing. You add it up, right? Even this is almost like extension of the leg. You just add it. You need to add this to get this. and you want this to be equal to this. That's it. So you can have as many as you want. It's the same method. Okay. So if you combine the two legs now with the two equations, they are both, one is BHP equals FPP, the other one is FPP equals BHP. Now combine them, and you get this. DPP is almost always represented by SPP, standpipe pressure, I told you that. CPP is represented by the mud return line, atmospheric pressure during normal drilling operation. And when we have, it's called the choke pressure when you are shut in, and you are going to see why. It has to be because the mud, when it returns, it doesn't go through the mud return line. It goes through the choke. That's why SICP sometimes it stands for choke pressure or casing pressure. Same thing. It's the annulus. It's the pressure on the annulus on the surface. Of the annulus on the surface. Example problem number 4. An 8,000 feet TVD well was filled with 9.62 ppg mud when it was shut in due to concerns for a kick. Reservoir fluid influx in the bottom of the annulus. This is what is a kick. It's a bad thing. What should be the SIDPP if the FPP is 5,500 psi? Now, I know that the formation pore pressure is 5,500 psi. What will be the SIDPP? Now, what leg do you want to use for that? Do you think we should use for that? The left or the right leg?
Left.
Left. Why the left and not the right?
Because it is the one measuring the SIPP.
It's the same.
Huh?
The same.
No.
Well, can you use the right leg?
I think in here we are talking about one fluid.
Left
Oh,
is
left.
left.
And then you need to talk about the
Left is
SI.
pipe.
Same
Yeah,
thing.
the pipe,
So the left will work. Why wouldn't the right work?
The right,
Yeah.
because we are
We are
given.
talking about SIDP.
Okay.
I think
But also,
another reason is we are not given two fluid with different density.
yeah, you don't have enough information. You don't know the depth of this.
Yes.
It can be whatever, and you don't know the length of this, and you also don't know the SICP. Okay, perfect. So this is the equation that I'm gonna use. It's SIDPP, the surface pressure, plus 0.052 times 9.62 ppg times 8,000 feet is equal to 5,500 psi. The only thing I don't know is SIDPP, right? So one equation, one unknown, solve it, and you get the answer to, I have 1,500 here, psi. Okay, because 0.052 times 9.62 is 0.5, so 8,000 divided by 2, 4,000 psi. So it's like doing 4,000 psi plus SIDPP equals to 5,500 psi. Very easy to solve, right? Any questions? Okay. What does SIDPP being bigger than 0 mean, like this case? What does it mean if it's bigger than 0? SIDPP being bigger than 0.
It's not atmospheric.
Well, it's not atmospheric on the drill pipe side. It can only be, well, generally it's atmospheric on the SICP side.
Yeah.
If you are, but what do you think physically SIDPP mean?
We don't have a kick. Means the mud weight is more than the.
No, the opposite. It means that the mud weight alone is not enough to hold the formation pore pressure. Because it basically tells you that this is not enough to hold this. You need extra. You need the 1500 extra. So it's an indication that you probably took a kick.
How much we need extra?
Huh? The 1500 SIDPP.
Doesn't it mean that we need like 4,000 extra?
No. 4,000 is given to you by the mat. This mat here weighs 4,000, but your FPP is
Okay.
5,500.
Yeah.
By shutting in the well and allowing the pressures to increase, to stabilize, not necessarily increase, depends. You are forcing this BHP has to be equals to FPP.
Can you explain that again?
Yeah.
You're saying that it means that the mods over there cannot are not enough to
So the mat alone, how much does it weigh? It weighs 0.052 times 9.62 times 8,000.
Yes.
So the mat alone, it weighs 4,000, but the formation I'm drilling in is 5,500. I'm short 1,500. Now I shut in the well. When I shut in the well, I force this BHP to be FPP. Okay? When I'm drilling, it may not be the case. If it's not the case, it means I'm having a kick. I'm taking a kick. But when I shut in the well, I force it to be balanced. It cannot be balanced if this is not giving me what I'm missing, and it's giving me that 1,500 amount I am short of, right? It tells me how much I'm missing, right?
So that means if it is reading 1,500, that means that's what you need to balance the pressure
Yeah.
level.
The math is not giving me that value that you gave me, basically. I need to add it. So it's not enough, it's not heavy enough. So, and this is why I got a kick.
And so what math are you supposed to add to balance it?
You need to add math such that that's a good question, actually. It's gonna come up. You need to make the math density high enough such that this, yeah, is giving you basically 0. This becomes 0. So you need to make it such that 0.052 times the new math, we call it the kiloweight math, times 8,000, it will be 5,500. And I don't know the answer to that off the top of my head. It will be higher than 9.62 for sure, right? So, example problem number 5. It shouldn't show this thing up, but anyway. In the same way as in example problem number 4, what would the SICP be if the reservoir fluid column in the annulus, it has now been confirmed that the well received a kick, because you know that you had a kick now, has 12 ppg density and is 200 feet tall. What leg would I use for that? The right leg. Do I have all the information now I need? To write one equation that has only one unknown, SICP. Everything else would be known. So I need to take, what I'm saying now is that this plus this plus this equals to this. Okay, this is what this equation is saying. So SICP, which is unknown, times 0.052 times 9.62. Now, the whole well is 8,000 feet, right? But the yellow is 200. Okay, so 8,000 minus 200 for the purple, right?
Yeah, so you subtract that from the
Good, right? Okay, plus 0.052 times 12, which is the yellow, times 200. Okay, and I calculate something that is 1475, right?
Yeah.
Does it make sense? Okay, now, good question. What does SICP not being equal to SIDPP mean?
The mod is circulating.
It's static. I shut it in. There is no, they are both shut in pressures. So it's no flow.
Oh.
Okay. Not equal.
Yeah,
If they are not equal.
That means there's a pressure on the casing.
No, there is a pressure, but there's also a pressure on the drip pipe.
so it means that the wall is certain.
It
Like-
means that the well, okay,
Yeah, I was gonna say that the mud went through the port, like it has a mud cave.
no, it means that you have different fluids on each side of the well on average, on the drip pipe side and on the annulus. So if you had imagine if you had the wrong mat weight, it was too small, but you didn't have a kick. How would that look like when you shut the well?
Can you come again?
Yeah, you didn't take a kick, but you have the wrong mat weight. How would it look like if you shut the well? Will it be positive or zero, the SIDPP and the SICP?
It will be positive.
Yes. And how will one side compare to the other? You have purple on both sides.
Mhm. So that means on the other side, there's going to be a kick showing that there's
It's
formation
coming,
fluid.
but you haven't taken it yet. You will get a kick because you have the wrong mat weight, but you don't have the new fluid inside that yet. So the whole thing is purple.
Mhm.
So what does that mean like? That the surface pressure will be
Equal.
equal. Okay, it will be equal if you have the same fluid on each side. Okay, ideally they're equal to zero because you have the correct.
You have the correct, yeah.
Okay, but you don't have the correct, it's wrong. So now they are not equal. You have one side that is bigger than the other. Okay, what if the SICP is bigger than the SIDPP? What does that mean?
It has a fluid with higher density.
Yeah, which one is the
Oil.
The formation fluid,
the formation fluid has a higher or lower?
higher. No, which one is
In
greater?
this case, this one is well, I said, what if the SICP is bigger than the SIDP?
It means the formation fluid density is higher than that of the.
No, it means lower. Lower. It's lower because it means you need more pressure on the casing side to keep it. It's like imagine if this hypothetically this is gas, it weighs zero. Okay, so basically I have this plus this to be equal to this. This doesn't weigh anything, hypothetically speaking. Okay, so this value would be very, very high because you only have this and you need to add to this to get it equal to this. So it would be a very high value. Now imagine if this yellow fluid is mercury, like very, very, very heavy fluid, very heavy fluid. Okay, you have this, which is very heavy, to be equal to this. So what you are missing is very small.
Very small.
Okay, is it possible?
That the value is small.
Yeah, but the value would be smaller. Is it possible to have SICP smaller than the SIDPP?
That's if the formation density is higher than the mud density is possible.
Yeah. So the idea is that I can have a heavy oil reservoir, very low pressure, or I can have a very low gas reservoir at a very high pressure, right? It doesn't matter, the fluid type determines the density, the weight of the fluid, but the pressure of the reservoir will determine if I'm going to have a kick or not, right? Versus what I am putting in the. So it's basically to make your mind understand that I can have gas, which is very low density, very light fluid, at a very high pressure, and get a gas kick. In fact, gas kicks are very, very dangerous. Okay, very, very dangerous. Why is it dangerous? Because then that yellow is very low density in something very high density and it's moving up like a balloon. So it's bringing pressure from the reservoir up in the surface. So you have basically, you shut the well, but it's still moving, it's creeping on this, coming up, you know? So you are really, you have to make decisions fast. But you can also have a very heavy oil in a very low pressure as well, or a heavy or a high pressure. It is completely irrelevant. The density raw fluid 2 versus FPP are very different from each other, right? FPP is what is the pressure of my reservoir? Raw fluid 2 is how heavy is the fluid of this. Very different. It's very different. Very, very, very different.
But
Yeah.
I don't think, because if we are looking at the weight of the formation fluid that we enter, I don't think any one of them can be higher than the mud density. Because either gas or oil, they are both lighter than
No,
water.
because what will determine, why did you get a kick? And we are going to see that later. Maybe it's a little bit of a premature mention that I made. But what will determine that I get a kick or not is that my BHP was smaller than my FPP. My FPP doesn't care what kind of fluid it is. It cares as in what density. It cares how pressure, what was the pressure of that fluid. That's why I got a kick. Once it's in my well, for my YouTube stuff, I care about how much how heavy it is, right? So it's the kick, it's its pressure that put it into my well, but now it's its density that matters for me, right? The raw fluid 2 is what you matter, this one. And how do you really know this one, to be honest? Like, very hard to get. These two values are very, very hard to know. Very, very hard to know. It's just for this, okay, static fluid level we're gonna see next time. Yeah, is that matters. I uploaded the homework, is due on Friday, next Friday, and I will go through it on Tuesday. You should be able to do most of it so far. It's very easy, so you need to use it as an opportunity to make a good grade, so that if the other ones are harder, you have made a good grade on this one. And I will have office hours on Tuesday, but after the lecture on Tuesday, you should be able to. There is only one small thing that is missing that we haven't done yet. Yeah, it should be easy. And YouTube model, yeah, it's applicable to every different scenario that is very, very useful. But it's, yeah, I mean, it's not the solution. It helps you derive the equations to find the solution. So that basically you don't memorize these equations. You memorize how to use the YouTube model to get the equations that you need in your exam to solve them and find the right answer. And yeah, the other important thing is that it's a little bit counterintuitive that FPP and raw fluid 2, or the yellow fluid density, completely unrelated, right? I can have a gas reservoir of very high pressure. FPP is very high. The density is very low. Or the other way around is possible. I can have a heavy oil depleted reservoir, very low pressure, heavy density, right? Because once it's in my well, I care about how much the column weighs. That's the idea. Thank you very much. I will see you all on Tuesday. Have a nice weekend. Thank you, Donald.
Thank you.
They are kicking us out, so I guess I will stop it. Oh, thank you, Tito. I didn't see you.